Hello, ladies and gentlemen. We're going to be taking a look at the Doppler effect today, sometimes called the Doppler shift. And many of you have probably experienced the Doppler effect before without maybe knowing what it's actually called. But today I'll have you go through your exit ticket. Don't forget to do the assignment. And then I don't have this on here, but just as a reminder, your test is also tomorrow. Remember, this is a shorter unit. So your test is going to be tomorrow. You can watch this video quick. This is a video of the Doppler effect, and it's kind of that apparent frequency change that you experience if you were standing on the side of the road and you have a car honking, like in this video. It kind of, as the car is coming towards you, you hear a higher pitch, and as the car is moving away from you, you're going to hear a lower pitch. So it's kind of that apparent change in frequency. All right, so go ahead and watch that video. All right, and then just to kind of give you a visual of how this is working. When we're dealing with the Doppler effect and we're talking about sound, the velocity of sound itself is 343 meters per second. We'll always use 343 meters per second. Sometimes 340 is used. I usually just stick to 343. And what happens here is, since sound can only travel at 343 meters per second, and you have a car, let's say, that's honking its horn, that is traveling at a fraction of that speed. So let's just say this car is moving at 26 meters per second. So it's moving at a very, very, very small fraction of the speed of sound. But even though it's moving at a small fraction, that means that what you're going to have is you're going to have all these waves that in front of it that are essentially not going to be spaced as far apart. Okay. Because it's going 26 meters per second itself. So unlike something that would just be stationary, if you just had a car sitting here stationary, this is my car. I know it's a very poor drawing. If you had a stationary object honking its horn, all of the sound waves would be traveling at 343 meters per second in both directions, and they would be evenly spaced apart. Well, now since you have the car moving in one direction, now those sound waves are going to get bunched together in front, just due to the fact that sound can't, the speed of sound can't stay ahead of it, if that makes sense. And the exact opposite is true for behind the car. So now you're going to have larger spaces between each wave because basically the speed of sound, it can't keep up, because now you're basically adding on the speed of sound plus that 26 meters per second that the car is moving. So when you have this, all these waves that are bunched up together in front, you get a smaller wavelength, which then means a higher frequency. So that's why when a car is driving towards you honking their horn, it sounds higher pitched. And then after it passes by you, now all those waves are going to be spread farther apart. So they have long wavelengths and lower frequencies. So then it's going to appear that it has a lower pitch to it. Okay. So that's just kind of the breakdown of how that works, sort of how the Doppler effect itself works. So let's get into our equations. There are a couple different scenarios that we have. I'm just going to put the speed of sound back up here. There's a couple different scenarios that we have when we're dealing with the Doppler effect. The first one is where you have a moving source, and that's what this traditional one is. When you have a moving source, you're going to use this equation. Now, let me break down each one of these variables real quick. The first variable right here, f prime, or frequency prime, that is going to be your, let's call this, I was going to call it apparent, but let's just call this, that's not what I want. let's call this observed frequency. And then this frequency right here is going to be the actual frequency. Okay, and then you're going to take the actual frequency and divide it by 1 plus or minus the velocity of the source. So like here I used an example of 26 meters per second divided by the velocity of sound, which is that 343 meters per second. Okay, so plugging in the numbers itself is pretty simple, but when it comes to figuring out the plus and minus, that's when it can get a little bit tricky. Okay, because what we have to do is we have to kind of take into consideration our knowledge of fractions and how that works. So you think about how a fraction works, and what we're changing here in this specific fraction is we're changing the denominator. So if I'm going to add, so let's say I'm going to add, I'm going to be increasing the value of that denominator. And when I increase the value of my denominator, what that's going to do to my observed frequency is it is going to decrease that observed frequency. All right. So that when you add is when it applies to source moving away, is when you'll use addition. All right, so then obviously by process of elimination, you can say that when you decrease the denominator, now it is going to, so we'd be using minus here, now that is going to increase the observed frequency. So that's what we would use for the source moving towards you. So then you would use minus. Okay, so those are the two situations that we would use for a moving source. All right, now let's take a look at what we would use for, so that's a moving source. Now we can take a look at a moving observer. Very similar situation. The only difference is instead of dividing, now we are going to be, because the wavelength is constant, now we are going to be multiplying. There is one equation that you can use for every single given situation if you would like to, and I'll show you a link to a video that explains that. If you would rather do that, I think it's easier just to use these equations, but I'll let you make that decision for yourself. Okay, so for this situation, all of my variables are still going to be the exact same. But now let's think about in terms of whether I want this to, whether my observed frequency is going to be larger or smaller. If I am walking towards the source, okay, I am going to have a higher observed frequency. Okay, and the reason for that is because if you think about, let's just say these waves are passing by every 1 second. Well, if I'm walking towards it now I'm actually going to be encountering those waves in less than a second, so the frequency is going to be higher. Okay, now I can say the exact opposite is true. If I am walking away, now I would have a lower observed frequency. Okay, so let's take a look and let's think about this if we want to think about either adding or subtracting. If I add to this, what that's going to mean is I add this number to my 1. So whatever you find for this fraction here, and I add it to that 1, that's going to create a higher observed frequency now because we're not dividing, we are multiplying. Okay, so for the higher observed frequency, for the moving observer, now we would use addition. And then for the lower observed frequency, because we would be subtracting and we are multiplying, that would end up giving us lower observed frequency. So when you are walking away, you would use minus. Okay, hopefully that makes sense. Let me know, guys. Let me know if you guys have any questions on that. And then our final situation here would be is if we have both a moving observer and we have a moving source. Okay, now this is the equation where if you wanted to, you could use this for any given situation. You could use this for a moving source or for a moving observer if you really wanted to. And the reason you could do that is because for either your observer or your source, you would end up getting just 0 meters per second. So you'd be adding or subtracting 0, which wouldn't really matter. But I'll let you watch that video if you want to try to use that equation for everything. All right, and that video is right down here at the bottom. This guy does a really good job of explaining that. All right, so let's take a look at an example though. Everything here is going to be the exact same in terms of our variables, right? And I guess this one doesn't show it here, but these two V's right here, those are my velocity of sound. It doesn't actually say sub-sound there, but those are 343. So it says you are traveling in a car at 55 miles per hour or 24.6 meters per second. So let's just say this is velocity of u, the observer, is 26.4. And then let's say that we have a second car moving towards you. So we have the velocity of the source is also equal to 26.4 meters per second. All right, its horn is sounding at 475. Okay, so that 475, that is going to be our frequency. That's our actual frequency. Okay, so if we go to plug everything in here, so we're looking for f prime, which is our observed frequency, is equal to 475. And I'm just going to go ahead and plug in the numbers, and then we'll talk about the addition and subtraction afterwards. So we will have 343. And then the velocity of the observer, 26.4. Right? And then 343 again, and 26.4 again. All right, now we got to figure out, do we want to use plus or minus in the numerator, and do we want to use plus and minus in the denominator? Okay, well, what I want you to think about is this just kind of goes and combines those two problems before that we were talking about. So if you as the observer are moving towards the source, okay, well, what did we say if you, the observer, is moving towards the source? Right? Well, what we said is then we are going to actually add, okay? Because remember, by adding those two, right, that is in your numerator, so that's what we are multiplying by, so that is going to make it bigger. Remember, when you are moving towards a source, you're going to have a higher observed frequency, okay? Now we think about the source, right? When we had a moving source. Now, if we think about the source moving towards you, what am I going to want to do? If the source is moving towards you, it is going to have also a higher frequency. So in order to make this denominator down here, in order to make that a higher frequency, we're not going to want to add, but we are going to want to subtract, because the smaller the denominator, the larger your answer is going to be. So now I have everything plugged in, and you can go ahead and solve for that. And I will do the same because I actually don't have this one solved for right now. All right, so hopefully you all got an answer of 554.2 hertz would be your observed frequency, and that's due to the combination of you driving towards the sound source and the sound source also coming towards you. So therefore, you're going to get a much higher frequency than it is actually making. Okay, hopefully that makes sense. Watch that video if you want some more examples and some more clarification on that. I have a quick video here if you want to go ahead and watch that video for any of those of you who have seen The Big Bang Theory before. And in this episode for Halloween, Sheldon actually dresses up as the Doppler effect and nobody really understands it. So hopefully maybe now you understand that a little bit more. And then finally, as a reminder, do your assignment and your exit ticket, and then your test will be tomorrow. If you have any questions, send me an email or a private message on Google Classroom. Have a great day.